Creatures swim freely in pressures that would implode a human body in seconds. Our lights are traumatic flashbangs to eyes that have never known dawn, and most of Earth's living volume has never seen the sun we trust. One correction before we go further. A human body at depth wouldn't crumple like an empty submarine hull, because most of our tissues are water, and water does not compress. What fails first are the gas-filled spaces: lungs, sinuses, middle ear. Those cavities are designed for a world where gas surrounds the body at low pressure. Compress the gas, and the walls fold inward. University of Illinois physicists put it directly. The pressure from the water would push in on the person's body, causing any space filled with air to collapse. Pressure in the ocean rises by approximately 1 atmosphere for every 10 meters of descent. That is roughly the pressure of the entire atmosphere above you at sea level, added again with each 10-meter step down. NOAA puts the pressure near 500 atmospheres at 5,000 meters. In the deepest trenches, it exceeds 1,100. A snailfish, an amphipod, a squid, or a jellyfish moves through that water without a metal hull and without any structure resembling one. This isn't magic. These animals have different solutions to the same physical fact. Many deep fishes abandon gas-filled swim bladders entirely. Inflating a swim bladder against increasing pressure becomes harder with each meter of descent, so deep water species often achieve buoyancy through gelatinous body layers instead. Research on 9 deep-sea fish species found their gelatinous tissues were more than 96% water. Those tissues are less dense than seawater, which is enough to generate lift. They are also cheap to grow, requiring little protein or lipid investment compared with dense muscle or bone. In Hadal snailfishes living below 6,000 meters, the gelatinous layer runs thickest just behind the abdominal cavity and along the posterior body. When a live specimen was modeled robotically at Monterey Bay in 2009 for locomotion experiments, adding the watery layer outside the tail caused the robot to swim faster. The tissue wasn't just buoyancy, it was also shaping water flow, reducing drag, functioning as something between a fin and a fairing. A body that looks loose and unfinished to us may be precisely assembled for a world where every structural material costs more than an animal can easily acquire. Molecular chemistry also changes. TMAO, trimethylamine N-oxide, is an osmolyte that appears in high concentrations in deep-sea invertebrates and some fishes. Research from the Journal of Experimental Biology showed that TMAO can prevent pressure-induced unfolding and proteolysis in lactate dehydrogenase, an enzyme central to energy metabolism. At 101 atmospheres, enzyme function in shallow water fish degrades significantly. In deep water scorpaenid relatives tested at comparable pressures, TMAO reduced that damage. It's a chemical cushion against an environmental force that would otherwise unmake a protein's shape. And yet, a review in Current Biology states plainly that the physiological mechanisms allowing organisms to adapt to extreme conditions of the deep ocean, high pressures, food shortage, lack of solar light, are still largely unknown. The adaptations are visible. The molecular logic behind many of them is still being assembled piece by piece. That incompleteness is one reason the deep sea keeps generating forms that seem unreal. We see the result without fully understanding the pathway. The old shorthand, that we know more about the moon than the deep sea, has cultural staying power but limited scientific precision. It mixes unlike categories: lunar topography, seafloor terrain mapping, direct biological observation, species cataloging, and human visits. The Conversation published an explicit assessment of this claim, concluding it's at best about 70 years out of date as a comparative statement about knowledge. The gap that remains is real, but it is measured differently. NOAA Ocean Exploration has reported that 28.7% of the global seafloor has been mapped with modern high-resolution multi-beam sonar. That statistic measures bathymetry, terrain shape and depth, not direct observation of anything living. NOAA also estimates that less than 0.001% of the deep ocean seafloor has been visually observed by explorers. Not sampled, not surveyed, not acoustically detected. Actually seen. To compare those two numbers, nearly a third of the seafloor terrain is geometrically known, while the fraction that a human eye or camera has actually looked at is so small it fits within a rounding error. That is the frontier. Not a rhetorical one, but an empirical condition where large regions remain visited only by the organisms that live there. The Hadal zone below 6,000 meters is the most extreme example. WHOI put it directly. Extreme pressure is one reason why the ocean floor remains largely unexplored. Reaching Hadal depth requires vehicles built to survive pressures equivalent to stacking a city block of water above you. Fiber optic tethers thin as a human hair, transit times that can span days. Woods Hole's Hades project in 2014 described its goal as conducting the first ever systematic comparison of trench life with neighboring abyssal plains, because before that effort, the scientific record on trench biology came almost entirely from brief, opportunistic visits with trawls and camera landers. What that means biologically is that for most of the ocean's living volume, life has been sorting itself out under conditions humans never witness. And the constraints driving that sorting become more severe the deeper you descend. No constraint is more immediate than light. Water absorbs visible wavelengths unevenly. The long end of the visible spectrum, red and orange, gets filtered first and most rapidly. Blue-green light travels farthest through clear seawater. This isn't decoration, it's geometry. A photon at red wavelengths carries slightly less energy than a blue photon, and it interacts differently with water molecules. Red is absorbed as heat. Blue-green is absorbed far more slowly, which is why open ocean water appears blue rather than the full spectrum of sunlight. The depth at which red disappears varies. Water clarity, dissolved organic matter, suspended particles, and the angle of incoming sunlight all shift the numbers. A coastal bay with high particle load dims and reddens everything faster than clear tropical ocean water. But as a general progression, NOAA describes red light as largely absent by 100 meters in typical ocean conditions. Underwater photographers find that photographs taken without artificial light at 10 to 20 meters already show an image with all warm tones flattened, leaving only blue-green. For animals, this shift isn't aesthetically neutral. A red animal at the surface reflects red light and appears red to any observer whose eye responds to red wavelengths. Descend below the red cutoff, and there is no red light to reflect. The same red pigment now sends back nothing. The animal appears dark, potentially black. NOAA describes this precisely. Without red light available to reflect, red animals appear grey or black, becoming nearly invisible to other organisms. The bloody belly comb jelly demonstrates the outcome in one of the most striking ways available to a soft-bodied animal. Its body cavity is vivid red, a colour that would stand out in almost any shallow water environment. At depth, Monterey Bay Aquarium explains, the red appears black and blends into the surrounding dark. The comb jelly isn't hiding the way a flounder hides against sand. It's disappearing into a wavelength that no longer exists in its environment. The Atolla jellyfish lives between roughly 1,000 and 4,000 meters. At those depths, red light has been absent for hundreds of meters above. WHOI notes that this makes the jelly appear completely black to predators. Its soft body, its tentacles, its entire architecture read as a gap in the water rather than an object. Some deep-sea fish take the strategy further, achieving surfaces that reflect almost no light at all. Research published in 2020 described fish in the genus Oneirodes and related groups with skin reflectance below 0.5%, some approaching 0.04% reflectance across all wavelengths. The mechanism involves densely packed arrangements of melanosomes, the pigment-containing structures in skin cells, arranged to trap and absorb rather than scatter incoming light. At that level, the skin absorbs effectively any wavelength that reaches it. The fish does not merely appear dark, it reads as the absence of a surface. But the ocean's visual problem does not end with pigment. Imagine looking upward from below, through dim water, toward a faint brightness coming from above. Any animal suspended in that water column would cast a shape, a darker outline against a slightly lighter background. This silhouette problem affects every mesopelagic organism in the twilight zone, roughly from 200 to 1,000 meters. The dim, downwelling light creates just enough contrast that a predator looking upward can see the shadow of prey it couldn't see any other way. Counter-illumination is the biological answer. If an animal produces light from photophores on its underside, directed downward at a brightness and color that approximately matches the light falling from above, the contrast between body and background reduces. The silhouette that would otherwise advertise the animal's position becomes harder to resolve. Among squid species, photophores on the ventral surface are common enough that the Wikipedia entry on counter-illumination treats the mechanism as one of 3 dominant underwater camouflage strategies alongside transparency and silvering. The UCSB bioluminescence web describes it this way. Many squid have their lower ventral surfaces covered with small, light-emitting photophores that put out a soft glow when the squid turns them on. Smithsonian identifies it as an adaptation enabling deep-sea animals to hide in an environment with few hiding places. The limits are genuine. A predator with precise enough vision can resolve individual photophores if it gets close enough. At 8 meters, unlit fins and tentacles remain visible even when the main body is well matched. Counter-illumination isn't invisibility. It's a reduction in detectability, which, in an environment where detection usually means death, can be sufficient. Firefly squid, Wattersinia scintillans, carry 3 types of photophores on their ventral surface. Small dermal photophores scattered across the underside, larger photophores clustered around the eyes, and very bright photophores at the tips of one-arm pair. Blue and green emissions are both present. Research in 2025, presented as a preprint, found that firefly squid adjust their green photophore expression in response to social presence, modulating the ratio of green to blue output in ways consistent with a coordinating signal during group activity, such as mass spawning. Their spawning is visible at the surface. Each spring, from April to late May, millions of females rise from their usual 200 to 400 meter habitat into the shallows of Toyama Bay, Japan, to release fertilized eggs. The bay fills with shifting blue-green light that local fishers and tourists travel to witness. Journalists who have covered the event describe it as undulating constellations of glowing blue stars, changing shape with every fin flutter. From the shoreline, the display looks decorative. From below, in open water several hundred meters down, the same lights serve a geometry of concealment. Yet counter-illumination operates in the twilight zone, where some light still reaches. Go deeper and the problem changes. Below the photic zone, the threat from above diminishes. No downwelling light creates silhouettes. But predators still hunt, and prey still need to find food, in near total darkness. This is where the dragonfish found a different use for wavelength. Among stomiid dragonfishes, specifically Malacosteus niger, Aristostomius, and Pachystomius, researchers documented a system of far-red bioluminescence. Malacosteus niger emits light from a suborbital photophore, the organ located beneath the eye. Its emission peaks around 705 to 710 nanometers. That is well beyond the red wavelengths that sunlight carries to even the shallowest ocean zones, and far past the blue-green range where most deep-sea visual systems operate. An eye tuned to those wavelengths will register far-red emission poorly, if at all. Malacosteus niger's visual system is modified to detect that hidden color. Its retina includes red-shifted visual pigments. An astaxanthin-based layer behind the retina acts as a reflector, giving photoreceptors a second chance to capture incoming photons. And a photosensitizer derived from bacteriochlorophyll, a compound normally associated with photosynthetic bacteria, shifts sensitivity further toward long wavelengths. A 2016 study published in Scientific Reports confirmed that this photosensitizer originates from the fish's diet, rather than from bacterial symbionts living inside the retina, as earlier hypotheses suggested. WHOI's outreach page for the stoplight loosejaw captures the dietary link in plain language. The fish derives its ability to see red light from its favorite snack, copepods, which accumulate the relevant compound from their own diet. The result is a creature that carries a searchlight nobody else can see. Its suborbital photophore illuminates nearby prey in far-red light. Prey animals, operating with blue-green tuned visual systems, are likely unaware of that illumination. The dragonfish sees them lit. They don't see its light. The Proceedings of the Royal Society B study on this system was titled Long-Wave Sensitivity in Deep-Sea Stomiid Dragonfish with Far-Red Bioluminescence, a measured title for one of the more precise biological tricks documented in the deep ocean. Two caveats matter. First, the trait is documented in specific stomiid lineages, not in all animals called dragonfishes. Second, researchers haven't established that the far-red emission is completely undetectable by every other deep-sea organism in those waters. The qualified framing is that it is relatively hidden from eyes tuned to shorter wavelengths, which, given the optical arms race underway in midwater, may be sufficient. Taken together, the light story shows a progression. In shallow water, color is rich and light is abundant. In the twilight zone, the spectrum narrows and silhouettes matter. In deeper mesopelagic water, counter-illumination erases those silhouettes. Deeper still, some animals exploit a private channel of wavelength to hunt animals that can't even perceive the illumination falling on them. The same depth gradient that removes light also concentrates scarcity. Photosynthesis ends at roughly 200 meters. Below that boundary, the biological system depends on what falls from above. That material is marine snow, fecal pellets, dead plankton, discarded mucus structures from gelatinous animals, fragments of organisms too small to count individually, but dense enough to form visible flurries. Smithsonian describes the flakes as made up of poop from animals, decaying animals, and other types of organic matter that slowly make their way to the sea floor. NOAA identifies marine snow as a primary food source for many animals in the dark ocean. By the time marine snow reaches the abyss, much of its energy has been consumed by bacteria during the sinking process. What arrives is dilute, slow, and unpredictable. Waiting for it demands a different kind of animal than chasing krill at the surface. The vampire squid, Vampiroteuthis infernalis, is named for its red eyes, dark, cloak-like webbing, and the way it can curl its arms up over its body to reveal spike-like structures. Its Latin name translates to something close to vampire squid from hell. The name fits the silhouette, particularly in brief footage captured against a dark background. The ecology is different. Mbari states it directly. Instead of hunting down prey, Vampiroteuthis feeds on marine snow, a flurry of dead plankton, poop, mucus, and other organic material sinking from the waters above. The animal trails two long filaments that collect material as it drifts, then uses arm cirri to manipulate the gathered particles toward its mouth. Monterey Bay Aquarium describes it as a gentle scavenger. A global, stable isotope study involving 104 specimens from the Atlantic, Pacific, and Indian Oceans found that larger individuals occupy a trophic position consistent with opportunistic consumption of particulate organic matter. Juveniles showed greater mobility and more zooplanktivory. As the animals grew, their diet and movement pattern shifted toward the slow, detritivorous mode. The species occupies oxygen minimum zones between roughly 600 and 3,300 meters, layers where dissolved oxygen can drop low enough to exclude most cephalopods. Adaptations for surviving there include the lowest mass-specific metabolic rate among all cephalopods studied, hemocyanin with unusually high affinity for oxygen, and neutral buoyancy achieved without relying on a gas-filled organ. Every component of the vampire squid's physiology points toward energy conservation in an environment that does not reward excess motion. Its name isn't wrong exactly. Its appearance matches the archetype well enough. But an animal named for a bloodthirsty monster turns out to be living on what amounts to oceanic compost, in water that would poison most of its relatives, at metabolic rates low enough to wait out very long gaps between meals. Moving down the depth ladder, some animals carry anatomy that makes them look like surviving examples of very old design. Most shark species have 5 pairs of gill slits. This isn't arbitrary. Gill slit number is a reasonably consistent trait across most modern elasmobranch families. 6 or 7 gill pairs appear in the order Hexanchiformes, which includes frilled sharks, 6-gill sharks, and 7-gill sharks. The frilled shark, Chlamydosolacus anguineus, is eel-like in body plan, with a snout positioned so that the mouth opens at the front rather than underneath as in most sharks. Its 6 gill pairs are bordered by ruffled edges, giving the gills the appearance the common name references. Published range estimates from FishBase place it between 0 and 1,570 meters, with most records concentrated on continental and island slopes from roughly 120 to 1,500 meters. The frilled shark is routinely called a living fossil, which captures a genuine observation. Its body plan does resemble forms preserved in the fossil record more closely than most modern sharks do. But the term can imply that the lineage is static, which isn't supported. A lineage that has persisted is still evolving, still responding to pressures, still represented by living individuals that reproduce in modern conditions. Whether the extra gill slits specifically confer advantages in low oxygen environments is a more complicated question. Sources in the supplied research suggest this is likely, but acknowledge it requires more evidence. 6-gill and 7-gill sharks aren't restricted to deep, hypoxic habitats. Their anatomy is old in design, but their ecological distribution isn't simply explained by any single selection pressure. The barrel-eye fish offers a cleaner case where anatomy and function can be linked more precisely. Macropinna microstoma lives in North Pacific midwaters between about 600 and 800 meters. The first thing that surprises most observers is the pair of apparent eyes on the front of its face. These aren't eyes. Mbari identifies them as olfactory organs, structures for chemosensory detection, not vision. The actual eyes are the 2 green glowing structures visible through a transparent dome that covers the top of the fish's head. Those eyes are tubular, elongated along their axis in a way that gives them a narrow field of view but high sensitivity along the direction they point. For decades, the standard understanding was that the eyes pointed permanently upward, useful for spotting prey silhouettes overhead against the dim, downwelling light. Preserved specimens supported this interpretation because their tissue wasn't intact enough to show the full range of motion. In 2009, Mbari researchers published footage of living barrel eyes captured with remotely operated vehicles. The footage showed something that preserved specimens had hidden. The fish can rotate those tubular eyes forward when eating. An eye that gazes upward to detect overhead prey can also pivot to look directly ahead when food is within reach. The transparent cranial shield protects the eyes from contact with the stinging cells during that maneuver. The entire system, the olfactory organs that look like eyes, the actual eyes hidden behind a transparent dome, the rotation mechanism that shifts gaze from detection to feeding, makes sense only in the context of the specific hunting situation the fish has evolved to exploit. Not every strange feature at depth belongs to such a well-documented case. Big fin squid of the genus Magnapinna are recognizable from the few available footage clips by their extremely long arm and tentacle filaments, often held at right angles from the body before drooping downward. The filaments are out of proportion with the body in a way that looks unfinished or damaged to an observer expecting squid anatomy derived from shallower relatives. NOAA documented a big fin squid at 2,385 meters during expedition EX-2107 and states the genus can live deeper than any other known squid. Guinness World Records lists a Magnapinna observed near the seafloor at 6,212 meters in the Philippine Trench, Western Pacific. That depth lies below the conventional 6,000-meter boundary where Hadal Zone designation begins. The exclusivity claim that big fin squid are the only squid occupying Hadal depths is contested in the supplied research. Other squid taxa have been recorded at substantial depths, and the exact range of Magnapinna is incompletely documented. What can be said with confidence is that sightings of this genus consistently occur far below depths at which most cephalopod biology has been studied, and the animals almost always appear briefly, react to vehicle lights, and disappear before extended observation is possible. Their long filaments may be sensory extensions, feeding structures, or something researchers haven't yet characterized because no individual has been followed long enough in its natural state to document what those structures actually do. That kind of uncertainty appears again with body size. Deep-sea gigantism is real, uneven, and not fully explained. The BMC Biology Genome Study of B. jamesi notes that, similar to other deep-sea organisms, giant isopods have larger body size than their shallow water relatives, with large stomachs and fat bodies, presumably to store organic reserves. The word presumably carries weight. The researchers could sequence the genome and identify expanded gene families related to insulin signaling, thyroid hormone signaling, glycolysis, and vesicular transport, all consistent with large body size and efficient nutrient use. They found evidence for low basal metabolism, bulk food storage capacity, and mechanisms for making the most of intermittent meals. None of that tells us definitively why the lineage became large in the first place. Hypotheses in the literature include cold temperatures and reduced metabolic demand, intermittent food availability and the storage advantages of a large body, reduced predation at depth, oxygen dynamics, and life history constraints that delay maturation and extend growth periods. One study of deep-sea benthic communities distinguishes between gigantism in a minority of species and widespread size reduction in other deep-sea animals. Giant isopods, giant amphipods, and giant spider crabs appear in footage from abyssal and hadal environments. So do fish, barely a few centimeters long. Large body size is an answer in some environments for some lineages. It isn't the defining output of the deep ocean as a system. The cause of deep-sea gigantism, as the available research frames it, remains open. What keeps accumulating are examples of forms that science encountered late. In 1976, a US Navy vessel off Hawaii became entangled with a shark unlike any species in the scientific literature. It measured more than 4 meters. It was caught on a parachute anchor deployed from a research ship. The species was described as Megachasma pelagios, megamath shark, the sole member of family Megachasmidae. A large vertebrate, visible at the surface, had remained undescribed. Its discovery didn't reveal a monster. It revealed a filter feeder with a vast, soft-lined mouth that concentrated small organisms by swimming through them with jaws open. In the decades since 1976, only a small number of megamath specimens have been documented because the species spends most of its time in mid-water depths that are difficult to survey. The point isn't that megamouths are everywhere, it's that large animals can remain rare encounters when they inhabit mobile, three-dimensional dark environments at scales that dwarf the total area of human-accessible ocean habitat. NOAA estimates the ocean may contain 700,000 to 1 million animal species, excluding most microorganisms, with roughly two-thirds not yet formally discovered or described. That estimate carries uncertainty. Estimating the number of unknown species requires assumptions, but even a conservative reading suggests the catalogued fraction of deep ocean biodiversity is small. The largest biological movement on the planet illustrates how long such things can remain hidden. During World War II, US Navy sonar operators detected an acoustic layer that appeared to rise toward the ocean surface at night and sink again during daylight hours. The layer could resemble a false seafloor on screens that were supposed to be detecting submarines. Later research connected the phenomenon to dense aggregations of marine organisms, zooplankton, lanternfishes, squid, and other midwater animals, performing what is now called diel vertical migration. WHOI calls it the largest migration of animal life on Earth. Every day, these animals rise toward food-rich surface waters under the cover of darkness, then descend as daylight returns. The movement spans hundreds of meters, repeated daily by populations of organisms so dense that Navy sonar read them as solid mass. The phenomenon was known to exist before sonar. World War II made its planetary scale visible for the first time because sonar detected layers that echolocation had never resolved as a specific biological pattern before. The animals involved in diel vertical migration aren't hiding deliberately from scientists. They are responding to light, temperature, predation risk, and food availability, with movements that happen to occur at depths and times that make direct observation difficult. They connect the twilight zone to surface waters biochemically, exporting carbon and nutrients downward when they die, cycling elements through the water column on a daily basis. What the ocean is, seen whole, is a gradient. At 200 meters, a fish managing its silhouette emits light downward to match the faint blue-green glow overhead. At 400 meters, a firefly squid, normally invisible in this depth range, produces blue and green light from its underside, its multiple photophore types adjustable in relative brightness and wavelength mix. At 800 meters, a barrel-eye rotates its tubular eyes inside a transparent dome, looking upward for prey and forward for the moment to feed, under cranial architecture that wouldn't survive a collision with a siphonophore's stinging tentacles without the protective shield. At 1,000 meters and beyond, the atoller jellyfish floats black and invisible, red pigment present but functionally irrelevant in a world where red no longer travels. At 1,500 to 2,000 meters, a malacosteus dragonfish sweeps its far red searchlight across prey animals lit up in a wavelength their eyes weren't built to register. At 2,385 meters, a big-fin squid with arm filaments longer than its body holds those filaments at angles that make no intuitive sense to an observer. At 3,000 meters, a vampire squid drifts through oxygen-minimum water, trailing its collecting filaments through a slow snowfall of organic debris, metabolizing at the lowest rate of any cephalopod known. At 6,212 meters in the Philippine Trench, a Magnapinna squid, reportedly observed near the seafloor, sits at a depth that qualifies as hadal by most definitions. And at 10,047 meters in the Kermadec Trench, we have conducted what Woodhull describes as the first systematic attempt to understand what lives there at all. The progression isn't decorative. Each step represents real physical change in pressure, light, temperature, oxygen, food availability, and the mechanics of swimming, sensing, and surviving. Each animal at each depth is an answer to the actual conditions of that layer. Darkness selects for new visual systems or for abandoning vision entirely. Open water without cover selects for counter-illumination, transparency, ultra-black surfaces, or shapes that dissolve silhouettes. Scarcity selects for patience, storage, low metabolic rates, and diets that would seem unworkable to a surface organism. The creepiness is largely a projection. We bring to these animals a visual vocabulary trained on daylight, air-breathing bodies, clear horizons, and hunting behavior organized around speed and strength. The dragonfish's teeth look menacing because our brain maps them onto a predator it recognizes. The vampire squid's cloak looks threatening because the gesture resembles a defensive posture we respond to. The barrel-eye's blank forehead looks unsettling because we expect eyes where there are none. But the dragonfish's teeth belong to a particular jaw geometry useful in open water where prey can move in any direction. The vampire squid's cloak exposes spike-like structures that may deter predators, a threat display, not malice. The barrel-eye's face looks the way it does because both surfaces that might otherwise be used for eyes are doing other jobs. None of these animals chose their form. None of them experienced the encounter with a submersible the way we experience them. A 2021 study found that pelagic organisms avoided white, blue, and red instrument light when exposed to research vehicle illumination. The animals that appear on footage are animals responding to intrusion by a light source that has no natural equivalent in their environment. What we call alien is largely what happens when evolution runs under a different set of constraints for long enough. The deep ocean has had the same amount of time as the surface to accumulate adaptations. It has simply been doing so in conditions where light is absent, meals are rare, pressure is immense, and the only constant is cold. The deeper you descend, the more completely those conditions diverge from the surface world. Body plans, visual systems, metabolic strategies, and chemical infrastructure all reflect that divergence. Some causes, like why certain lineages became very large, remain genuinely unresolved, and the sources that describe gigantism leave that question explicitly open. The ocean isn't a finished catalogue. NOAA's maps cover roughly a third of the seafloor's terrain. The fraction of it that any observer has actually looked at is vanishingly small. Hundreds of thousands of species may remain formally unnamed. The largest daily movement of animal life on Earth went undetected until submarine warfare created tools sensitive enough to hear it. Going deeper does not lead to a monster gallery. It leads to a world where the rules of surface biology fail one by one, replaced by solutions surface mammals were never prepared to recognize as elegant. The further from the surface, the more completely the environment writes its requirements into the animals that live there. That frontier is still mostly dark, still mostly unvisited, and still generating new forms of strangeness every time researchers manage to look.